Hello, everyone, and welcome to Live, Laugh, LoLBAS. The goal of this talk is to provide some additional insights into how threat actors are leveraging living off the land binaries and scripts to be successful in their attacks. A quick overview of this presentation, I'll say a few things about myself, and then we'll talk about a few basic concepts related to LoLBAS, and then pretty quickly jump into an example of a well-known LoLBAS. After that, we'll talk about a few detection methods and techniques, and then finally we'll close out by talking about a fairly uncommon but pretty cool LoLBAS. My name is Matt 1T Lyons because my name only has 1T in it. I've been with the Optiv Enterprise Incident Management team for the last 7.5 years, most recently as a practice manager, but prior to that working as a consultant. During my time working as a consultant, I was able to lead or at least be involved in the majority of our threat hunting projects, as well as a good number of fairly large-scale investigations that took place over a variety of different industries and different sized organizations. Along with that, I've been able to work with our attack and penetration team on purple team projects. So between the two, I have a nice balance of experiencing attacks in a controlled, simulated environment, as well as real world examples. Outside of incident response, I love hiking, camping, driving tiny trucks, anything that gets me outside. On to some basic concepts and language so we can all be on the same page as we move through this presentation. LoLBAS, lolbin, lollib, lolscript. It's a whole lot of acronyms that basically mean the same thing. LoLBAS is living off the land binaries and scripts. lolbin is living off the land binaries. The idea of living off the land is simply that a threat actor can and will leverage programs that already exist within the environment. And one of the main reasons that they'll do this is it helps them avoid detection by dropping less artifacts to disk. By not introducing new tools into the environment, they're at a lower likelihood to trigger some kind of alert or detection to make defenders aware of their presence. And I'm not positive if there is some kind of established baseline or criteria for what makes something a LoLBAS, but this is kind of the criteria that I use most often. The first being that it needs to be present on the system by default or introduced through some kind of reputable installation vendor. A good example of on the system by default would be PowerShell. It's on most Windows systems. It's usually not blocked in a lot of environments either. And then an example of one that might be installed by a reputable vendor could be something like FileZilla. If your corporate IT puts that on the base image and it goes out to all the machines, it's there by default within that environment. For this talk, we'll mostly focus on Microsoft signed binaries that exist within the Microsoft Windows OS environment by default. But things like FileZilla, any kind of remote admin tool, those still fall into that living off the land category. The second criteria there is that it needs to have some kind of unexpected functionality. And that meaning maybe the original developer intended it for it to have this feature for some reason. But when it reaches us, kind of the end user, we're left scratching our heads wondering why this program can do these things in the first place. And then the last criterion, and maybe the most important for this, is that functionality needs to be useful in some way to a threat actor. Examples, but not limited to execution. Think your macro-enabled Word documents. Exfiltration, infiltration, anything that lets the threat actor remove data from the environment or introduce new data sets into the environment in an easy way. And then the last one, obfuscation. Anything that makes more noise, adds a layer of complexity, makes it harder either to alert or detect on something, or even just harder to validate an alert or a detection. But now that we've kind of established this baseline of what a LoLBAS is and why we're going to talk about it, let's look at an example. Squiblydoo. So not only is it just fun to say, but it also fits the category of a LoLBAS pretty perfectly. I believe in spring of 2019 or somewhere around that time, my dates may not be exactly correct, is when a lot of information around this was coming out, and it was very popular, and we saw it a lot during our investigations. And it makes a great use case of a LoLBAS. it hits criteria 1 pretty perfectly. This is present on the system by default. Reg server 32 and script object DLL are both Windows signed legitimate files that are going to exist in every Microsoft Windows system. Reg server 32 is used by Windows to register and unregister DLL files, and the script object DLL is used to execute these COM scriptlets. Usually it's going to be a .sct file. Criteria 2, unexpected functionality. These SCT files don't have to be located on the host's file system. They can be on the internet somewhere. And then criteria 3 is that functionality is very useful to a threat actor. So you run reg server 32, it calls script object DLL, and script object DLL, basically doing zero validation, runs whatever the contents of that SCT file are. So what does that look like? Well, using the Red Canary Atomic Red team as an example here, we can tell reg server 32 to go grab this SCT file off of their GitHub, and script object DLL is going to run the contents of that SCT file. The SCT file in this case uses JScript to call WScript to run calc.exe. Now, I think it's pretty easy to imagine that this GitHub page is actually a malicious URL, some piece of threat actor infrastructure. That SCT file contains something more malicious in it than calc.exe. It's telling it to go call a Cobalt Strike beacon and run it instead. And one side note as we move into detecting this kind of usage is that it's actually not that abnormal to see reg server 32 making network connections. So if we can't base a detection on that, what can we base a detection off of? But before we actually talk about detection, I like to kind of establish some basic foundational concepts before we get too far into it. So the first concept I want to talk about is the pyramid of pain. This was developed by David Bianco in 2013, shortly after Mandiant released their APT1 report. And the pyramid of pain is this simple idea that some things are easy for a threat actor to change on the fly and other things are more difficult. And the pyramid of pain basically just categorizes those by how much pain it causes the threat actor to change that piece of their attack or their infrastructure. So at the bottom of the pyramid, we've got hash values, the easiest thing to change. One character adjustment in your payload, recompile it, you have a new hash value. Congratulations, you've avoided detection. Next up, we have IP addresses. Again, very simple to change. Swap VPN, you now have a new IP and have avoided detection. Domain names, a little bit more difficult, but still in that realm of easy enough for a threat actor to adjust minor changes to their infrastructure and they're back on it. Up from that, we have network and host artifacts. These are a little bit more difficult for threat actors to adjust because a lot of them are going to be tied to the tooling that they're using in some capacity. And as defenders, we're able to identify those artifacts and track them down. Tools becomes even more difficult for a threat actor to change on the fly because it takes time to develop new tools. And then lastly, TTPs, which is your tactics, techniques, and procedures. And these are very difficult in most cases for a threat actor to change because this is kind of their ingrained processes of how they operate. And that's a very difficult thing to, one, adjust on the fly or even over time. So detecting on things higher on the pyramid causes the threat actors more pain. And most LoLBAS are going to fall into either TTPs or tools, kind of just depending who you ask. Next, we have the cyber kill chain from Lockheed Martin. Another conceptual model that was made to help defenders understand how a threat actor might move within the environment. This model is fairly linear in that in order to move to the next objective, a threat actor must have achieved their previous objective. But if you've never been a threat actor or never been on the red team side of things, you may not know how they operate. And that's the goal of this model, is just to help us understand, at least from a high level, what might happen next or what maybe has already occurred in the environment. There's an expanded version of this, the unified kill chain. It takes this concept, expands on it, and then integrates some things like the MITRE attack framework in it as well. And speaking of MITRE attack framework, we come to my most unreadable slide. But just like the previous two slides, it's more about the concept. The pyramid of pain shows us that TTPs can cause the threat actors pain, the most pain actually, and that the cyber kill chain and unified kill chain show us kind of how and where the threat actor might move on their next objective. And the MITRE attack framework takes that and breaks it all down into these little digestible chunks. And again, from a defender side, anything that we have to attempt to categorize or label threat actor activity is going to give us a bit of an advantage in our next steps for detection and prevention. So now that we've got those concepts covered, we can actually talk a little bit more about how they apply to detecting LoLBAS. And right here off to the side, we've got the MITRE attack technique 1218, which is signed binary proxy execution, basically just a fancy way to say LoLBAS. This list here has 13 different binaries known for that technique. I think the amount is probably closer to around 35 binaries that are well known for this technique. So how do we actually go about detecting this type of activity in the environment if these are expected files, if these are signed Microsoft files? The number one there is going to be some kind of EDR product in place. It's going to do a lot of process tracking and command line auditing, and that'll pretty much give you a lot of these answers. If you don't have that and you have room in your SIM, you can do something like enabling sysmon for kind of that next level of Windows event logging. You can also turn on some additional features within Windows event logging itself for some additional command line auditing features. The key part there is a lot of these LoLBAS require specific switches or arguments to be made in order for them to have that unexpected functionality. And by tracking and monitoring that, you can identify them. In some situations, the threat actor might leverage a LoLBAS and do something that is going to hit the network, whether that's outbound or laterally, in which case maybe something like your firewall, IDS, IPS, NDR will pick that up. But the most tried and true and effective method that I've come across is baselining. Just like the poster on my wall says, to find evil, you need to know normal. And so what I usually end up doing in a lot of cases, looking for LoLBAS in an environment is make a list of the LoLBAS you want to look for, dump all of those processes, all of those command lines, start deduping it, and then start reading through them and finding the ones that are standout, or find the ones that have those specific switches included in the argument. So let's take a little bit of what we know so far and play a game of malicious or not. So our first option there, pester.bat. Pester.bat is actually a PowerShell module that's present on most Microsoft Windows systems. Those help options are kind of your specific switches that need to be added. And then what's going to happen is it's going to run whatever comes after that null semicolon character there. So in this case, we would assume it's malicious, but without knowing the exact contents of that PS1 script, we can't say for certain. Next up, we've got scheduled tasks, a classic for persistence. And we've got it set up where every single day it is going to run this Google Update Task Machine UA task, and it's going to direct it at that Google Update.exe. In this case, most likely not malicious, but again, without the context of what that exe is, if we can't validate that that is the actual Google Update.exe, maybe it is malicious. Next on the list is for files, which I think is a pretty cool one. What this is going to do is it's going to look in the Windows System 32 directory. If it finds a file called notepad.exe, which it will, then it's going to execute the next command that's put in front of it. So in this case, it's going to look for Notepad, it's going to find it, and then it's going to launch this Wireshark exe, which again, if we can't validate that that is a real Wireshark executable, then this could be malicious or may not be. And the last one on there is bits admin. Really cool functionality in that one. You can download tools, bring them into the environment with bits admin. You can also execute payloads with it. And in this case, it's using bits admin to go out to the Optiv GitHub, grab the Scarecrow files, and drop them in a temp directory. I would say this one is malicious, but I also wouldn't expect a threat actor to grab a .go file and drop it to disk. So let's dig a little bit deeper into the detecting and how we would investigate a LoLBAS to begin with. So here we have a scheduled task being set up to run PowerShell to call a GPO update.ps1 from this user's desktop. Looking in our unnamed EDR console here, we can see that that command.exe process being run. We can see it setting up the scheduled task in that same command line that was on the previous slide, if we dove into that process specifically. As well, we can also see that there is a child process associated with that of scheduled task.exe running. And if we look into that scheduled task.exe running, we'll see within that there are some file modifications being made related to that GPO update.ps1. Now, something we would likely want to do if we were investigating this would be get a copy of that .ps1 file to see what the contents were to make some validation of if it was malicious or not. If we can't get a copy of that .ps1 file, maybe the tool we're using in this case, again, our EDR console, is able to show maybe some more process data related to that PowerShell execution. So tracking down that PowerShell execution, the command line arguments being made, we can see that that scheduled task when it runs is making a network connection to a host within our environment and grabbing a file from that host. That's our Splunk.exe there. Now, we can't say for certain whether this is malicious or not. It is very suspicious, to say the least. But without a copy of that PS1 file, without a copy of that executable, we can't say for certain one way or the other if it is malicious, which is part of what makes LoLBAS so effective. Now, maybe we don't have access to an EDR product, or maybe the EDR product's not installed in that subset of the environment. What can we do then? We can gather a lot of that same data through event logs or through Sysmon. So if you're pulling down your event logs from your hosts, you would still be able to track this information. We would see this scheduled task being created. We would see that it has a strange name. We'd see that it's using a command to launch PowerShell to run this .ps1 file. And again, that might then give us the information we need to investigate this host further, get a copy of that PS1 file, find out the contents of it. If we're also doing command line auditing on things like PowerShell, we'll be able to validate if that PS1 file successfully ran or not. And here in another unnamed EDR console, we've got an alert around run DLL32, another known LoLBAS. And in these screenshots, you can see that the alert details are for run DLL32 launching an unusual file. But as a defender, you may come to the realization that .cpl files are not that unusual for run DLL32 to be launching. But what is unusual is for those to be launched from the desktop. And so depending on the backend rules of this alert and how it's being triggered in the console, simply relocating that .cpl file may be enough to avoid detection in the future. A great example of these kinds of minor adjustments causing tooling to not trigger alerts is on this slide. So in our first example, we're running MSHTA to launch a Cobalt Strike beacon from a remote source as a .hta file. In the EDR console, this did trigger an alert. I believe the original alert was triggered only because the HTA file was a web connection instead of being hosted locally on the file system. And then in the second alert, we have the exact same Cobalt Strike beacon and payload, but this time it's been turned into a DLL file and dropped locally on the host, which didn't get picked up either. And then after that, it was installed using MSI-exec, which did not trigger an alert. So we have the same payload. We have two different LoLBAS, two slightly different techniques, one being detected and alerted on, and the other one being missed completely. So up to this point, we've talked about and looked at a few examples of some LoLBAS, some well-known, others less so. But I wanted to close this out with one that we don't see a lot, but I think has some really cool potential, and that's hh.exe. So hh.exe is a Microsoft signed native on the operating system file. And it's used to open CHM files, which are usually help documentation files, and it uses a compressed HTML format, and it's pretty cool from that perspective because you can bundle a lot of different things inside that file type. Similar to our script object DLL, HH basically does no data validation of what's inside those files when it runs. And for whatever reason, when it was developed and put together, they decided that it should also be able to launch PowerShell scripts for whatever reason. So here we've got three different examples of using HH. That first one, it's remotely connecting to another host in the subnet and just arbitrarily launching a PowerShell script. That one is a Sandcat command and control beacon. And then the next two examples, it's reaching out to Amazon AWS servers. It can run HTML. It can also run that CHM file type. Some of these can get a little messy depending on how they're executed. Some of them actually have prompts show up for user interaction. I'm sure there's a way to get around that though. So what are our takeaways? What are the things we need to be paying attention to? What kinds of tools are already on the hosts? What are our IT admins? What are our operations teams using to perform their tasks? What kinds of tools may already be in exclusions list that need to be reevaluated? Maybe they can just be a little bit less broad, restrict specific switches or arguments that relate to LoLBAS. And then finally, an alert in a tool is not the same as detecting that an attack is happening. What kinds of false positives could be coming from LoLBAS or a fake false positive that's flying under the radar, right? So if Word is launching a .chm file, is that legitimate or not? Is that a user opening the help documentation, or is that a macro-enabled payload using HH to pull down a file from a remote source? MSHTA, there's a few legitimate HTA files out there that are web hosted that may need to be called. How are we validating which ones of those are real or not within our own environments? I appreciate everyone taking the time to listen to me talk about LoLBAS. I think they're really interesting. There's always something new and cool coming up with them. And they're just a really great thing to be familiar with and learn within your own environment. I'll stop there and open it up for questions.